I want to conclude the long carbon part. Remind ourselves we have one more geologic lesson after that, and it's called abrupt climate change. And we'll talk about that a little bit. Before we get too far here, I would like to review the last exercise because I was ambiguous in my instructions, so that didn't lead to a lot of good answers. And then there was a thing that I was looking for that I didn't see too often, so I'm just going to go through that. So I screwed up on asking the question, so that made, I want to clarify what I did screw up. So here's the, no, that's not what I wanted. Okay, this is it's out of order. So here's the assignment we just did. I monkeyed around with CH4 and CO2. I was having you run the slugulator. And what's the slugulator? Dump a bunch of stuff in all at once and see how it attenuates. That's the bucket of water. The bucket of water with this particular model could be CO4, a CO2, or CH4. Doesn't matter. They react a little differently. The details are different, but the exercise could be the same. Basically, we had an awful lot of good responses to whatever you did, whichever way you did it, and it didn't matter, or describing what you did. But let's look at the question carefully. By pre-describing this very specific number of gigatons, that set up the problem. The question is, why did I pick 269 as a model? I could have picked anything. And what I was really looking for is the fact that buried deep, and now it's like, it's buried deep, and I didn't point it out explicitly, that's the amount of carbon that we theoretically have left to burn. So we've been playing a dumping game, but our bucket isn't completely empty yet. We could dump a little more. So the exercise then was, if you would dump the whole bucket and there was no way to continue burning fossil fuels, how would the system flush itself out after that? And then this particular model will tell you that. You could have gotten a similar result. I mean, you wouldn't have gotten a similar result. CH4 could read differently, but we still had the same problem. Why did we pick some number? Okay. The second question was about tweaking a knob to find out how it behaved. And I don't know if all of us found the little point that the little cursor, if you hold the cursor over the curve, it'll give you the right number. And so when that's very handy with an exponential. But we had two populations, I think. One that would get something close to 125 gigatons. But then there were some that were kind of way off. And I don't know, the units were different and there were some other issues. So if you have one of those, then I'd be happy to talk to you about it. But this is the kind of question that you can ask in a model. And that's what people are doing nowadays. All right, this one, what I was really trying to get at is what do we care about 250 years from now? At some level, the carbon that we've got in there in the atmosphere now is not going to go away in 250 years. What's the significance of that realization? I mean, do we care about it or don't we care about it? A lot of us had an answer that said, okay, the raise in carbon can change the temperature, and then that can impact, besides sea level, all kinds of things. And that's all actually happening today. So why do we care about 250 years from now? It really hasn't manifested. One reason I would say personally is that the full effects of the changes that we've made haven't yet manifested themselves. In 250 years, they may or may not. But it's going to be an evolving game for a while. So everybody comfortable with evaluations or any questions that we could do to tidy that up? Okay, let's go back to what are we trying to do today. If we are committed to this certain level of carbon, and I think I will make that case just as an operating assumption if we haven't convinced you already, that we are talking about the long term. We didn't talk about anything much longer than a few thousand years. Archer talks about 100,000 years to actually permit. beyond a few hundred years, it doesn't matter. But what do we want to do anything about it? And there's an intrinsic part of us that says yes. And if we answer yes, then we have to ask what. Now, if you don't answer yes, then the rest of the lectures doesn't mean anything. And for the sake of argument, if you say, no, we don't need to do anything, fine, but humor me and go along that there should be some options of what to do. Those options are fairly limited in a broad sense. I would say that they're basically option one, don't do anything. Learn to live with it. That's an adaptation strategy. Okay? And that's not exactly do nothing to learning, but it's more about learning to adapt than it is to try to address the cause that you need to adapt to. You know, is it better to work with the symptoms or the disease? Is that right? Yeah. Are you more worried about what is the manifestation or why it's manifest? And so, in this case, you don't care. You just need to learn to live with it. Okay. The second thing is, if you do care about the thing, you want to try to remove it. If we've got to put too much CO2 in the atmosphere, let's take it out. You hear all the time strategies and plans to take out CO2. And I'm going to contend, this is sort of the summary, but I'm going to basically contend in a couple of slides that that's pretty well underway, and it's more of an economic challenge right now, or an economic question than it is anything else. The third option is you could figure out not some way to address the problem, but to address the resulting energy balance. CO2 in the atmosphere is a certain amount, it's not enough to change, it'll change plant respiration a little bit, it'll change the chemistry of the oceans a considerable amount. But in terms of most of the things we're focused on living on the surface of the planet, it's radiation balance. So option 3 would be take a new direction and cut off the monkey around with the energy balance. Okay? For today's exercise, we don't need to, I'm not going to talk much more about that. I'm going to briefly mention this and then set it aside, but the assignment set around this one is far more controversial. I want to present you options that are harder to deal with. We've been fighting politically for the last 3 decades about reducing CO2 emissions. And for 3 decades, the emissions have done this. There's no real reason to expect that the emissions are going to be curtailed in any large fashion in the next couple of years. They might be. They're going to make some incremental progress, but because our demand for energy is growing faster than our curtailing CO2 emissions or the use of fossil fuels, the fossil fuel still consumption is going up. And it will be. So these are the things to deal with then. Basically, how do we want to live in this high CO2 in the atmosphere world? And they're rhetorical, and they're all expensive. They're all bad. Which one's the least bad? All right. So there's where we're going. Questions there. We did that. A couple definitions to get us started with. There's a concept out there called geoengineering. And in this case, geo is not geology, but it's the globe. And so we're talking about engineering or a manifestation of something that's on a global scale. And so if we look at and this is Harvard, which is a big name, but this is the Harvard Solar Geoengineering Research Program. And they define 2 things here. One is geoengineering refers to the set of emerging technologies. They don't exist yet. I would make one exception to that. They could manipulate the global environment and partly offset some of the impacts of climate change. Okay? We're not going to learn to live with climate change. We're going to do something to address it. Solar geoengineering, in particular, could not be a replacement for reducing emissions or with coping. it could supplement these efforts. So Harvard's basically saying we got to do a bunch of things. It's not A or B, it's A, B, C, and D. And then let's further talk about two kinds of geoengineering as Harvard does. They have solar in here for a reason. If you read this business, conveniently, I'm not sure I'd split into two broad categories. The first is carbon geoengineering. And by that, what they mean is also called carbon dioxide removal, taking stuff out of the air, taking the existing CO2 levels and reducing them somehow. And there's a range of techniques for that. And that was my option 2. Or the other component is the solar engineering, which Harvard's big on doing, or thinking about at least, not doing it. Fancy term now is solar radiation management, and which would also mean things about albedo or sunlight or some way to manipulate that energy balance. One is taking CO2 out, one's messing with the energy balance. The idea is to manipulate either of those to get under some less extreme temperatures. I put out these definitions because I'm gonna want you to deal explicitly with this one, which is option 3. This one again is called carbon capture and sequestering. And these names keep changing. People change these names for whatever reason. But it used to be just geoengineering was this one, and then this one was this one, and now this blah, blah, blah. So geoengineering as a search term isn't going to do you any good. It'll give you too much stuff. Geoengineering is how many different things of engineering? 2. Off the top of your head, which one would you think would be more practical to do? Messing around and taking around the carbon, or screwing around with the energy budget of the planet?
Screwing around with the energy, I'd say.
Screwing around with the energy of the planet? Think that would be more simple?
Not simple, but I feel like it has a better end result.
Okay. Good. Then you're on game with the thrust of the exercise. I'm going to talk, because it would be remiss not to talk about the notion of carbon dioxide removal. And I would point you to an article that came out basically just now, or 2 days ago, from the National Geographic. Unfortunately, it's buried behind a paywall, so I can't assign it to you. But it does go through the notion that there's a lot of efforts underway. It lists them, and there's various approaches. And part of the carbon capture and storage challenge is there's a capture and then there's the storage. There was a TED talk on how do you capture it, and what they're thinking of doing is they're running air through these filters, and they're capturing on some sorbents on some material, a resin, the CO2, and then they peel it off the CO2. Now that technology in itself is quite far-fetched. The chemistry is easy, but the guy on the TED Talk says, think about a square meter box. And to remove a ton of carbon dioxide through that square meter box, you've got to take a length of carbon dioxide 2,000 kilometers and drive it through the box. That's in part, that's really because the CO2 is so really dilute. It's 400 parts per million. 400 parts per million is high for CO2, but it's not very concentrated. So the capture, people are working on the capture. Most of them have this sorbent, some sort of what we call, if you're looking it up, artificial trees, the notion of scrubbing the atmosphere. A lot of them are designed around the notion of you let the wind blow something through, because you can't pump it fast. If you pump it, you're going to require more energy than you're going to get out of it. The second part of it is where do you store it once you've got it out? You get it out in a form, you've got to turn it into something. And it's a gas, and generally they turn it into either the liquid phase, which keeps it cold, or they combine it with something. And it turns out there's rock type called basalt that's chemically, makes a nice comparison. You combine basalt and CO2 and you get a different phase of rock, and you can get rid of it. So the other general storages arguments are underground. And one of the interesting things about the storage underground within this whole broad categories is that one of the industries that's very attuned to getting involved in this are the oil companies. The oil companies have developed a good technology to get a hole in the ground. So they're saying, okay, if you pay us enough, we'll take care of your carbon dioxide by putting it back in the ground. Not a bad business model, actually. There was a big thing a few years ago about where do we want repositories, and to actually store the carbon right, you need a certain kind of geology. And Ohio and Kentucky were examined extensively to find some place to put it. I don't think anything in Ohio was necessarily optimal. I think there were some Kentucky ones. All right, so at any rate, this is a public article that's germane because it came out today, I think. And unfortunately, though, it's not that easy to read, but it would tell you, be a darn good summary to get going on that topic. If you did look into those, you'd see that there's a lot of different ways, there are companies now doing this. It used to be venture capitalists or private philanthropists that were funding individuals to do it. And again, the low concentration is a problem. But these things are now companies, and they're actually at a loss, operating to start sucking or removing scrubbing the carbon from the atmosphere and sticking it someplace. And therefore, I think this is more of a question of economics than it is of technology. The technology is not great right now. One talk I heard on this by a guy who was into this, he had a business model that said, okay, well, the first thing we got to do is find out who uses CO2, and it turns out it's an important industrial gas, and we'll make it and make sure that they buy it. And so the industrial gas that's okay, I'm not sure where I was going with that. But at any rate, there is an economic value of C14. So that's about all I'm going to say on option 2. Now, to try to counterbalance it, we want to dig into a little deeper. So this is, again, the energy, solar radiation management. Sounds technical, but it means the energy balance. Can we remember what goes into the energy balance? That was, that was like 8 weeks ago in this term, or something like that. Global energy. We always did it with little arrows. And the arrows are going through where? Are they going through the earth? Were they going through parts of the earth? Where's all the energy come from?
It's from it was the one with the sun and all the arrows that go to the equator.
All those arrows with the sun. All of the energy that we have is basically the sunlight energy, circulating around and around. Okay? And are we in balance with the sun?
No.
How so? Why are we not in balance?
Actually, I'm confused by the question.
Okay, so one of the hidden assumptions that we talked about earlier is if you put a bunch of energy in there, it can't absorb it forever, it gives it back off. And then for the wavelengths of energy that we're talking about for the sun coming in, there's something called the black body. And so basically some things, when they have energy, they glow. And so the energy can come in and pile up, but then it's going to glow and be re-emitted. And this is the basis of the short and long wave that become into the greenhouse effect. So we want to intentionally do some large-scale global manipulations of this balance. We've done that experiment once. This is called, by putting CO2 in the atmosphere, we've discovered that Arares 100 years ago was correct, that changes the surface temperature of the Earth. Okay, can we do something more directed now is the question. And if we could, or if we thought about it, what could possibly go wrong? And this is sort of my philosophical thing, that I would argue that we may not have enough information or insight to actually do this, but that's just me. So this notion of even trying, messing around with the solar radiation, we're gonna see different, you're gonna find ways to do it. I'm not gonna go into the specifics of the way, but 15 years ago or something, there was a convention of a large group of people at Harvard, and they basically said, no way that we should be messing with this. It's too risky, there's too many unknowns, we don't know enough, there's no way to effectively manage it, and the potential offshoots are too scary to consider. For example, one of the ones that they raised was, if you mess around with the energy balance, by definition, you're gonna change where the rain falls. And so if you decide as a global experiment you want to change the energy balance, but you change the rainfall coming into some area that gets wet today and turns it dry, they're not going to be happy. So they said no. 2 years ago, the National Academy of Science, which is the guiding, it's an independent set of academics who address very broad questions and try to publish a series of reports about it, particularly to the US government. In theory, the US government pays attention to the National Academies, and in practice they don't so much. But they said, maybe we need to look at it. Last summer, slipped in one of the budget bills that you may or may not have noticed. There's now a geoengineering, I'll show it in the next slide. There's money to start a geoengineering program, not to do it, but to think about it. So there's a lot of debate whether this is a good idea or not for technical reasons, but the US is starting to move ahead about thinking about it. All right, what are the specifics, and then what side you fall on are what we want to do for the assignment. So here's just an example, the National Academy report. Maybe cautious, we should look at it, and they outline the notions. And so here's this diagram that we saw the sun coming in, the shortwave radiation, the long-wave radiation. If you want to mess with the radiation balance, you want to take out you could theoretically block the amount of sun coming in. You could increase the amount bouncing back out, or you could increase the amount of long-wave radiation going out. Those are large-scale projects, so you have to have a whole part of the globe involved in. Here's the news blurb from last summer about there's now a program in the US federal government, at least, to start thinking about the problem. And you saw Harvard's solar geoengineering. They have a whole program. I don't know if it's a school or a department or whatever, but they have a whole department that's part of it. And if you don't think Harvard's not going to make some money on this. Okay. More recently, another group of 50 people said, let's not mess with it again. So it's contentious. Again, the arguments are basically, we don't know what's going to happen. If you do any of these things, we don't know enough about how the feedbacks on the climate system work. All right. Lady, was it pink thing? So what else do we need to know about geoengineering or solar geoengineering?
I guess, what ways are they actually, in reality, gonna try to do it?
What ways are they gonna do it? That's the homework for you to find out. There's a variety of ways, there's many different ways, and I'm basically asking you to look up a couple of them and then pick one and go into it a little deeper. Okay, so there's ways to do it. Like anything, the broad goal is to change the energy balance. Like I outlined on the other slide, you could talk about them coming in or let more out or whatever. What do you need to know more before we go much further?
What people are thinking about these long-term impacts might be, or they're guessing could happen.
Well, I think that's part of the homework too, is to figure out why there's pros and cons to anything, of course. So I'm asking you to focus in on one of the problems, one of the techniques, not all of the disadvantages. One of the disadvantages that well, there's a couple disadvantages that I can see. One is some of the techniques, if you start doing them, that's fine, and they might work. But if you stop, then the whole thing falls apart. The other problem, that's a conceptual problem. Cost is always a problem with these things. One of these involves like moving stuff up into space. And you can get a number for how much stuff you have to move in space and basically put an arrow up there. And then I would have people calculate how many shuttle flights, because the shuttle was moving stuff into the space that it would take. And now with the Starship, the much bigger capacity, it's an obscene number of rocket launches. But that's kind of some of the counterpoint. Cost and risk and who knows whatever. Okay, we want to look into number three. I argue that number 2 is underway. If you do a general search for geoengineering, you're going to get an ugly mess. If you restrict it to, if you go to the Wikipedia page on social engineering, you're going to see a nice list of stuff. That's where I would start. But I also start that whatever you find on Wikipedia is just the first branching point. But there's a menu list there that you could pick out and do that. Okay, keeping in mind, right now, we need to reduce emissions, that we're arguing, we need to reduce emissions. We're trying to figure out how to learn with elevated carbon. We've now tried to think about removing the carbon. It's not economic yet. I'm taking you to the next esoteric level of the one that nobody can decide whether we should do or not. I do that to emphasize how complex this problem is. So my proposed solution for the rest of the day is to have you start looking at that and make sure that you find at least one that you're comfortable, and so effectively do the first part of number 1 and run it by me so that I make sure that you're okay, and then you can get out of here. If you want to stay for all 3, that's fine. But I'd rather you spend time on this than me talking. I think you're going to learn more by researching it than me walking through the lists. Is everybody okay with that concept? All right, so again, probably the Wikipedia page on solar engineering is the best way to start. Does anybody need access to the internet? It doesn't have it. Maxine, you have access?
Do we search them online, or we have a specific paragraph for that?
Say that again, please.
Do we search the solar
Yep. Geoengineering.
geoengineering just online? And
If you get to the Wikipedia page that covers that, it has a very nice list of the specific ways to do that under the broad umbrella. My thing is for you to look at 3 different, there's more than 3 approaches, but pick 3 and dig into them a little bit deeper.
like pick them from a specific paper or just from the internet?
From the internet, but I'm suggesting that the Wikipedia page has a good list of them. So that'd be the easiest place to find out what they are.
You mean PDF pages?
Excuse me?
You mean PDF
Oh,
page?
Wikipedia.
Wikipedia. Oh, Wikipedia, I got it.
Wikipedia, sorry.
I got you.
I'm suggesting you start there because it's not comprehensive, there's others there, but it's got them kind of organized, so you, otherwise you're gonna get into kind of a morass.
I see.
There's some that have been around for years, there are some that are totally fantasy, there are some that are being acted upon. For the online section, I'm gonna truncate the video at this point. There's no point in you looking at the screen for another half an hour or so. But I would suggest that you find the first one, do the first exercise, email me that, and I can give you some feedback on that. That would be your option.